Okay, so I figured I'd start out with today's lecture by talking about the last quiz. Now, a lot of people took different approaches to this quiz. When it comes to synthesis problems, I suggest that you always work backwards and start with the functional group that you have. So here, our functional group is an alcohol. And also, if you notice, around this alcohol, we have stereochemistry on the two adjacent carbons. When you have the stereochemistry on the two adjacent carbons, that suggests one of two things. Either hydroboration or epoxide chemistry. Because these two reactions have control over the stereochemistry. Hydroboration adds the OH and the H syn to each other, and epoxide chemistry adds the OH and a nucleophile anti to each other. All the other reactions that we have that adds OH to an alkene, well, they don't have any stereochemical control. I'll give an example of that in a little bit. So let's take a look at the hydroboration example of this. If this was made by hydroboration, what that means is the OH and the H were added syn to each other. Well, if the OH is a wedge, this is a dash, but those aren't in the syn relationship right now. So to figure out what the starting material was, the molecule really needs to be redrawn so the OH and the H are syn to each other. When you do that, it means that deuterium becomes a wedge. This butyl group becomes a dash. This deuterium becomes a wedge. And this butyl group becomes a dash. Remember, these are the same molecules. The only difference is this is a different conformation. The OH and the H are drawn syn to each other. And this helps find what alkene was used, because here the two deuteriums are both wedges. So they end up cis to each other on the alkene, like so. And the two butyl groups are both dashes, so they end up cis to each other. Now we have an alkene. And one of the ways we have to make the alkene is to basically use D2 and Lindlar's. We want to use this one as opposed to lithium and ND3 because this is a cis alkene. And when we're trying to make cis alkene, Lindlar's catalyst comes in awfully handy. Now, it might be helpful to actually number this 3, 4, 5, 6, 7, 8, 9, 10. Because where the alkyne goes in the starting material, that's where the alkene is. So 5 and 6 are here. And then we can just draw in the others. So we have the alkyne placement correctly. Now, a couple of errors that I've noticed on this step on the quiz. A lot of people were drawing this product like this. Please, please, please don't do this. These carbons are sp2 hybridized. That means they are trigonal planar. And this structure right here, all 4 of those atoms circled, or actually 6 of those atoms circled, must be in the same plane. And here, the carbons are in the same plane, but the deuteriums are not. But for the correct answer, the deuterium, carbon, carbon, deuterium, and carbon all have to be in the same plane. So please, don't put wedges and dashes on alkenes. It's likely to be wrong. And that has to do with the hybridization of the carbons. Another mistake that people often make is they drew their carbon chain like so. And then they just drew in their alkyne. Again, this is incorrect. Because carbons 5 and 6 are sp hybridized. Sp hybridized carbons are linear, not bent. And so we did take off points for that as well. So please be careful when you're drawing these things. And then it's just a matter of making alkynes. And the way we have to make an alkyne is basically we make the carbon-carbon bond next to the alkyne. And so we split it at the single bond. The sp3 carbon gets a leaving group like a bromide. The sp carbon gets a sodium. A lot of people were making a mistake. They weren't drawing this, but instead they were drawing it 1 carbon short. This is wrong. It's a triple bond to a sodium, and that don't do. You could have drawn it like this, and this is okay. So either one of these two is okay, but just don't draw the triple bond to the sodium. And so this has 1, 2, 3, 4 carbons. And it's non-ionic, so we don't have to make it. This has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6 carbons. So we do need to make that. And the way we make this species is adding sodium amide. Common mistakes we saw with this was drawing it like this or drawing it like Na-NH3. Each of these is incorrect. And then this molecule can be made. It's an alkyne. We can make that carbon-carbon bond. Again, this has 4 carbons, so it doesn't need to be made. This has 2 carbons, but it's ionic because of the sodium. Therefore, we need to make that like so. Okay, so that's what we were looking for the answer to the quiz. With that said, there were quite a few other possible answers and so forth. In fact, there were quite a few answers that involved chemistry that we hadn't even talked about, and I'm not planning on talking about. So here is one such answer. I believe about 12 students came up with this answer, and so that's good that they're working together, or they all found the same website. I don't know. And I'll accept answers that involve chemistry that we haven't talked about as long as it's correct. Like this first step right here. To make that alkene. This is what's called a McMurray coupling. And this is a reaction that's very tricky to pull off. And we're not going to talk about this in Chem 343 or even Chem 345. But this reaction works just fine, so we'll accept it. So that's not a problem. It's a very dangerous reaction, though. So please be careful if you ever do a McMurray coupling. They're not done that often anymore, but it's something to be very careful of. So this part is fine. This part here is incorrect. Due to the solvent being water. And we'll get to this later on because that will be the topic of today's lecture. And because this is incorrect, this wouldn't give you this product. If this was a starting material plus this, that would give you the alkyne. That's fine. It's just that this isn't the right starting material to do this reaction. Here to here, a lot of students use the platinum catalyst. Platinum is very reactive. It's very difficult to stop at the alkene. So prefer to use Lindlar's if you need to stop at the alkene. And then this last step is also incorrect for a couple of reasons. Actually, for the main reason is you get the diastereomer. Unlike hydroboration, this doesn't have any control. The mechanism of this reaction is to protonate the alkene to give them more stable carbocation. In this case, they're equally stable. I'm going to say that hydrogen was added from the top, giving you this carbocation. Now the water can add from the top, and that gives you this diastereomer. Or it can add from the bottom, and I already incorrectly labeled which diastereomer it has. Let me go back. Sorry. If you protonate this hydrogen, and the hydrogen ends up being a dash, you just want to match the product that's shown. Excuse me. If you protonate the alkene, the hydrogen from the back side, and the OH adds from the top side, you get this diastereomer. If the OH adds from the back side, you get this molecule here, which is the opposite diastereomer, the one you don't want. And so as a result, you get a mixture of anti-addition and mixture of syn addition when you use acid and water. And that's the same way when you use oxymercuration, demercuration, you get a mixture of syn and anti. Only the hydroboration gives you just the syn when you're adding H and an OH across an alkene. So we took off a point or two for that. Okay. So that's enough about the quiz. But let's talk about this reaction here, bromination of an alkene. This works for bromine and chlorine. It's easier to explain this when you're using a cyclic alkene. The product, when you add bromine with dichloromethane to this, is you get two bromines on there, and it's anti. We're going from an achiral material to a chiral molecule, so it's racemic. Dichloromethane is a non-nucleophilic solvent. Other such non-nucleophilic solvents are carbon tetrachloride, hexane, THF, diethyl ether, etc. Chloroform is another one. Okay? Here, solvent is important, and it's important for this reaction that the solvent be non-nucleophilic. And I said this also works for chlorine as well. In a non-nucleophilic solvent, such as chloroform, doesn't matter which one you use, so, the mechanism of this reaction. Is much like the mechanism for oxymercuration. Where the bromine, with its lone pair, adds to one of the two carbons. The pi bond goes back, attacks the bromine, and that kicks the bromide off. The resulting bromine then now has two bonds. And they're both on the same side to that. This intermediate right here is what's called the bromonium. Now, as you can imagine, that Br is a pretty darn good leaving group, being positively charged and in a three-membered ring. and the bromide comes and attacks and does an SN2 reaction to open it up. And when you do an SN2 reaction, you invert the alpha carbon. So this bromine was a wedge going up, your leaving group was a wedge going up. So your nucleophile ends up being a dash. Now if it attacked from the other side, he ended up with this compound. These compounds are enantiomers. Okay. Now, the mechanism for chlorination follows the same thing, except wherever you see a Br, you put in a Cl. So in case of acyclic dibromides, if you want to figure out how to make this product from an alkene, and you're using bromination. In fact, let's just go ahead and draw that just a little bit better. Let's move this over here, this over here. So say you were trying to make this dibromide from an alkene. The way you figure out which alkene you use is you have to redraw the molecule so the bromides are anti to each other. Because bromination and chlorination adds 2 Brs or 2 Cls anti to each other. So you draw them anti-coplanar. When you do so, this ethyl group is a wedge. This propyl group is a wedge. Both of them are wedges. So the alkene would be a cis alkene. So, let's scroll back to that student answer. One of the reasons why this answer is incorrect is the stereochemistry was neglected on these two bromides. One bromine is a wedge, the other one would be a dash. Okay? That's part of the reason why that this is incorrect. The other reason why it's incorrect is because a nucleophilic solvent was used. Water. And that has some drastic consequences. By nucleophilic solvent, I mean water or an alcohol, where R is a methyl group or a primary alcohol. Secondary alcohols typically don't do this reaction. And tertiary alcohols definitely don't do this reaction. But what happens in the reaction is that the bromonium ion is intercepted. What I mean by that? So in the mechanism, you get the bromination, forming the bromonium. Species. And that launches the Br- off. Now this is so reactive that before this Br- has chance to come back and take its place, water, which is a solvent, and there's more solvent than anything else, outcompetes the Br-. And water comes back and takes that proton off. Now water takes that proton off rather than Br- because water is a much stronger base than Br- is. If you had Br- take it off, I'd accept it. But really, water is the likely candidate. And get this. These compounds are what are called halohydrins. Now we're adding two very different groups to that alkene. So in this case, it doesn't matter which carbon is which because the two carbons are the same. But if we make them different by making one more substituted than the other, and you could do this reaction with chlorine as well, but we're just going to stick with bromine. That's the more common form. The mechanism you form the bromonium. And then it's a matter of what side the water attacks. This is akin to our other three-membered ring reactions, such as this species, the mercury species, or protonated epoxide. These are all very similar to each other in that you have an excellent leaving group in a strained ring system. So what's happening is in each of these, the leaving group is leaving slightly before the nucleophile gets there. That means that this triangle right here is a little lopsided. and it leaves the carbon best equipped to handle the positive charge. That carbon is the more substituted carbon. That developing delta positive charge on that carbon is what attracts the water to attack. Like so. Excuse me. So the product that you get is this product right here. Okay. Now, let's talk about some chemistry of these halohydrins. If you treat this with excess sodium methoxide and methanol, you get this product right here. Now, what's unusual about this product is first of all, it's doing a substitution reaction. You tried sodium methoxide on this compound right here, the major product. Would be the E2 elimination. The product above is even more hindered than this example, but yet it's giving substitution. Also, note the stereochemistry. Of the OMA group. it's the same as the Br in the starting material. The stereochemistry stayed the same. It wasn't inverted. So this is a kind of an unusual reaction, that it's doing SN2, doing a substitution when it shouldn't be, and it's also not inverting. Well, turns out it is inverting, it's just doing it twice. This is an example of neighboring group participation. You get this neighboring group participation when the beta carbon has a nucleophilic lone pair. So what's happening in this reaction? As the O- comes in to do the substitution or elimination, but the thing is, acid-base chemistry is far faster than substitution and elimination chemistry. So does the acid-base reaction. If you look at this O-, it's perfectly in the right position to do an internal SN2 reaction. That gives the epoxide. Now the epoxides are known to do just SN2 chemistry, and in base you're going to attack the less substituted side. In base you're going to attack the less hindered side. Followed by a protonation. And you get your product. So the alpha carbon really did invert. It just did a double inversion. Because we did an SN2 reaction right here. And then we did a second SN2 reaction right here. And that basically flipped the alpha carbon twice. Now the way to check this is basically try the reaction again, only don't use excess sodium methoxide, just use one equivalent of sodium methoxide. And if you do so, the major product that you get is the epoxide. So this is also a way of forming epoxides, where you can take an alkene, treat it with bromine and water, or chlorine and water if that matter, and then you can treat it with base, such as sodium methoxide, or sometimes we'll use sodium hydride, because this acts only as a base, not as a nucleophile. Like so. Okay. Now, this neighboring group participation is not limited to OHs. You'll find that you can do it also with sulfurs and nitrogens. But you have to be very, very careful with molecules like this. Because they also do neighboring group participation. But they are also weapons of mass destruction. These are chemical warfare agents. They're often referred to as mustard gases. Simply because of this internal reactivity that makes this electrophile very reactive. So reactive, it'll often react with stuff we don't want it to, mainly our DNA and skin and mucous membranes and a whole lot of stuff we'd rather not have react. This one in particular, it's also an anti-cancer drug. In addition to being a weapon of mass destruction, it's used to treat leukemia. Okay. So, be careful of these if you ever see these in a lab. They are very dangerous, causes basically blisters, severe burns. But they also have a tendency to react far faster in SN2 reactions than normal. And that's basically because they form this very reactive electrophile. And that's all the time we have.